Welcome to Lecture 6, Chapter 2. Here we're going to discuss how the challenge of managing power system, so the way we produce electricity, how the challenge of managing power system with high shares, high proportion of intermittent renewable energies can be met. So by intermittent renewable energies, we mean some of the renewable energies that are intrinsically time variable in the way they produce energy, such as wind power or solar energy. But I'll come back to that in a moment. The good news to start with is that the cost of power generation through renewable energies is declining very sharply as a result of at least two different effects. The first being technological advancements as a result of research and development. The second being the economies of scale as they progressively become more and more deployed in our energy systems. The cost of the solar photovoltaic cells in particular has declined very, very sharply in the recent years, as you can see on this graph. You can see on the graph that the cost per watt of crystalline silicon photovoltaic cells, so that is the main technology that is being used today to generate electricity out of solar energy, but I'll discuss in a moment which other types of technologies, potentially even more performant, could be used in the future. But you already see on that graph a very, very compelling decline in the prices of these cells. I mean, they went from 76 US dollars per watt in 1970 to 0.74 in 2013. An effect that is sometimes called the Swenson effect, and that should well ring a bell. I mean, it really looks like the Moore's law in the semiconductor industry. The cost of the wind turbines has also declined, although a bit more gradually. I mean, nothing as spectacular than the cost of the photovoltaic cells, but still a significant decline in the recent years. It's important to underline here that the price per watt of solar photovoltaic cells is not the same thing than the price of producing electricity through solar photovoltaic energy, which is sometimes called by the energy experts the levelized cost of energy, LCOE. And in fact, the price of producing electricity through solar photovoltaic energy remains more expensive than the alternative sources of electricity production, at least in many places. It's not the case everywhere. It's true that solar photovoltaic energy has reached what we have called in the previous chapter the grid parity. So the cost at which it is competitive with other sources of power generation. So solar photovoltaic energy has reached this grid parity in several regions and countries, but not everywhere and by far. So their costs still need to significantly further decline to enable eventually their very large scale deployment at a competitive cost. That being said, and it's an important point I want to make, going forward, the main challenge in relation to renewable energies is likely to be not their costs, but how to operate power system with high penetration of intermittent renewable energy. So what is that? I mean, what is really the problem, and how do these renewable energies really differ from the other sources of power generation we have today, like coal or gas or hydro or nuclear? And why does it make the operation of the power system more difficult and more challenging? Well, as I said, it's because solar and wind energy are intrinsically, in a way, time variable. For a very simple reason. It's because wind is not always blowing and sun is not always shining. So that's a defining characteristics of these technologies. But on the other hand, the power grid needs to be able to match energy demand and energy supply on a moment-by-moment basis to maintain the functionality of the power system, to make sure that each and every time you need energy, there is an energy source to supply and meet your demand. Traditionally, this is accomplished by using large generators such as coal-fired power plants or nuclear power plants to provide what is called base load power. And these stable base load generators are then complemented by flexible, readily dispatchable units of power generation such as gas turbines to make a system overall capable of, as I said, matching supply and demand at any point in time by the addition of baseload power and flexible, readily dispatchable units of power generation. But going forward, we need to find new low-carbon solutions to the issue of supply and demand balancing, because as you can see, I mean, we cannot in a world where we try to avoid the dangerous effects of human-induced climate change, and therefore in a world where we try to deeply reduce the energy emissions, we cannot rely on coal power generation and gas turbines to, or at least not without carbon capture and sequestration, to ensure the balancing of the energy system, and going forward dealing with the intrinsic time variability of some of the renewable energy. So how can we do that? How can we ensure power system balancing while meeting the constraint of deep emission reductions? Well, there are three main ways in which a power system with high penetration of renewable energies can be balanced while, again, meeting this constraint of deep decarbonization. The first one is that the intermittent renewable energies, so again, wind, solar, typical examples, can be complemented with other stable sources of low carbon power supply, such as nuclear power or coal and gas fired power plants, but with carbon capture and sequestration. That's very important. Not freely emitting coal and gas plus CCS. Or other example, hydropower for countries that have such a potential. Or we can also build a system that links the uncorrelated or that links negatively correlated sources of intermittent renewable energies, because that's a way of dealing with the intermittency of each type of renewable energy, by making sure that combined we don't have or this intermittency, or at least that we reduce it. So that was for the first broad category of things we can do to balance the energy and the energy supply and the energy consumption with high penetration of renewable energy. Second, there is also great potential to better adjust the time profile of energy demand to the time profile of power supply. And this is, broadly speaking, what we call demand management. And the truth is that the cost of demand management technologies have declined very significantly. So it's not so much an issue of cost going forward, but the main challenges are going to lie in information management, grid management, but also in setting the appropriate economic incentives for demand management. So this is something really interesting that has great potential to help operate power system with high share of intermittent renewable energies. But the truth is that it's not going to be sufficient. What will be absolutely critical is to improve our energy storage options. That's really important, energy storage. And there is already a variety of electric storage technologies that are known and have been demonstrated on a broad range of timescale, from seasonal to daily to hourly to second by second storage, because we need all of that to ensure the functionality of the power system. For example, large-scale pumped hydroelectric storage has been cost-effective in many countries for decades. But the problem is that it is not available everywhere. So it will be very important to develop other storage technology options, and there are currently a number of options being considered, such as batteries or compressed air or hydrogen. But it's also clear that further research, development and demonstration is going to be required to determine how best to match diverse storage technology options and their cost-effective applications, and how to commercialize these technologies at a large scale and at a competitive cost.